I am Project Manager Saim Bukhari. My objective is clear: design, build, and operate a high-capacity frozen food manufacturing facility from an empty lot. The cycle takes raw potatoes through industrial washing, mechanical shredding, precise blanching, and rapid thermal freezing until they emerge as packaged hash browns. This initial business case mandates a 50 million rupee investment, expecting a 28% annual return. Our strategy relies on local Punjab sourcing and an unbroken cold chain. The project charter dictates strict constraints: fully operational in 12 months, without exceeding the $50 million budget limit. The physical scope is heavily constrained. It includes all factory construction and specialized processing machinery, but explicitly excludes the purchase of a downstream distribution fleet. An operations project requires mathematically constrained boundaries and rigid success criteria established on day one. Without them, scope creep mathematically guarantees failure. This chart maps the work breakdown structure. It partitions the massive scope of building a factory into 9 distinct management domains, organizing everything from technical procurement to quality control into manageable work packages. Our operational strategy is to engineer a repetitive, high-volume assembly line. By running this exact process constantly, we systematically drive down the per-unit production cost. Communication is structured by necessity. Executive stakeholders receive high-level monthly reporting on budget and schedule, while the factory engineers require daily technical check-ins to maintain construction momentum on the floor. This risk register documents exact statistical threats to our timeline. The first row reveals a 40% probability of a raw potato supply shortage. We neutralize this risk by establishing multi-supplier contracts across different agricultural zones, so one farm's failure won't halt production. The highest impact risk is a cold chain breakdown. If freezers fail, the entire inventory is ruined. We mitigate this through dedicated backup generators and stringent service level agreements for immediate technical repair. Operational planning systematically identifies and eliminates variables before physical execution begins. With the theoretical planning officially approved by the stakeholders, we transition to the physical construction and outfitting of the facility. This network diagram tracks sequential dependencies, calculating which tasks must finish first. Tracing the critical path from site prep to final testing reveals our minimum completion time. With zero slack, the timeline is strictly bound to 32 weeks. Capital expenditure heavily favors physical infrastructure. 66% of the total budget is consumed immediately by the factory construction and the procurement of specialized food-grade machinery. This Ishikawa or fishbone diagram maps quality management, aiming to anticipate manufacturing failures before they ruin the product. Panning across machine and method branches, we identify defect sources. Worn blades create inconsistent cuts, and fluctuating fryer temperatures result in unusable batches. External environmental factors pose equal risks. High ambient factory heat or sudden power outages can instantly thaw and destroy the frozen inventory waiting for packaging. Physical execution relies on identifying and controlling thousands of tiny, interconnected technical variables simultaneously. Operating this facility requires 60 staff members, deployed across 3 shifts to ensure continuous 24-hour production. Looking at the procurement plan table, we divide our supplier strategy. Specialized foreign processing machinery is secured through fixed-price contracts to lock in costs, while local raw potatoes are secured through long-term agreements to guarantee steady volume. This schematic outlines the production process flow. It details a linear, 7-step assembly line layout designed specifically to prevent material backtracking and contamination. The line begins by receiving the raw material, passing it through industrial washing, and feeding it directly into the mechanical peeling and shredding phases. The shredded potato then enters the blanching phase. The thermal parameters here are absolute. The product must remain submerged in 90 degrees Celsius water for exactly 3 minutes to neutralize enzymes and ensure food safety. Next is the high-heat frying phase at 180 degrees, followed immediately by a rapid thermal drop. The product is fed into an IQF blast freezer, taking it down to -40 degrees in minutes. High-volume manufacturing is achieved by enforcing rigid, unvarying process parameters at every stage of the line. This aggregate plan schedule charts out how we mathematically adjust our workforce to meet seasonal demand fluctuations throughout the year. During slow spring months, we utilize a level strategy, keeping a baseline workforce of 40 staff and producing exactly what is demanded. During the winter peak, we switched to a chase strategy, bringing on additional staff and heavy overtime to maximize output. Maintaining production volume creates a strict inventory problem. We must balance the high administrative cost of repeatedly ordering raw materials against the high electrical cost of refrigerating excess stock. We solve this using the economic order quantity formula. We input annual demand of 1,080 tons, ordering cost of 5,000 rupees, and holding cost of 2,400 rupees per ton. The calculation resolves to 67 tons. Ordering exactly this optimal batch size minimizes financial waste. To further reduce holding times, we operate a just-in-time supply chain. Local aggregators deliver raw potatoes exactly as the previous batch runs out. This logistical timing is managed by the SAP Enterprise Resource Planning System. It calculates the exact bill of materials and automates purchase orders without human intervention. Long-term operational profitability is dictated by mathematically optimizing inventory intersections, not by human guesswork. This project schedule Gantt chart provides the physical tracking mechanism used to monitor our live construction timeline. Below that, the reorder point chart visualizes our inventory depletion. The sawtooth pattern demonstrates how our 7-day lead time buffer ensures new stock arrives precisely as old stock hits the critical minimum limit. To quantify project health at our June 2026 status date, we rely on earned value management calculations. We compare the planned value, the 25 million rupees expected to be spent, against the earned value, measuring actual work completed at 25.5 million. By checking the actual costs, we calculate a positive variance. We can mathematically prove the project is simultaneously 500,000 rupees ahead of schedule and 750,000 rupees under budget. True operational control requires abandoning intuition in favor of ruthless, real-time mathematical variance tracking. Looking forward, this forecasting graph applies a weighted moving average formula to historical sales data, allowing us to accurately predict future retail demand. To monitor ongoing manufacturing quality, this X-bar control chart tracks sample data. As long as the data points remain within the upper and lower control limits, we know the production process is statistically stable. Finally, this decision tree models a strategic choice for the year 2027, how to handle rapidly growing market demand. We compare two paths. Expanding the current factory requires heavy capital but yields a high expected monetary value. Outsourcing production saves upfront costs but delivers a significantly lower financial yield over time. Operations management is an infinite loop. It is a continuous cycle of strategic planning, rigid execution, and data-driven evolution.